So we talked about heat, and heat is the transfer of energy between objects due to the temperature difference. It's kind of a measure of energy. So Q is heat, and it flows from the higher temperature object to a lower temperature object. So if you have system 1 here, T1, and system 2 is the surroundings, if T1 is greater than T2, the hot heat goes into the surroundings. So the system is exothermic. Q is actually negative. If your system is cold and your surroundings are warm, the heat flows from the warm surroundings into the system, and that's endothermic. We always talked about endo and exothermic, and now we're going to put this as if Q is positive, it's endothermic, and if Q is negative, it's exothermic. Calorimetry is how we measure heat flow, and the device called is a calorimeter. Specific heat capacity is the amount of heat needed to raise the temperature of 1 gram of substance 1 degree C, or 1 Kelvin. 1 Kelvin degree, the difference between 1 degree C and 1 degree Kelvin, they're equal. They're just transplanted by minus 273. So for energy changings, okay, so it's only usable, this calorimeter, within a certain state of matter, liquid, solid, or gas. We're not changing phases right now. But for energy changes involving phase changes, like melting to freezing, boiling to condensing, those are called heat of fusion, and that's enthalpy, or heat of vaporization, enthalpy of vaporization. So when you're melting, you're putting energy in, heat of fusion is going to be positive. When you're freezing, so this will be positive. When you're melting, you're putting energy in, and freezing, the enthalpy will be negative because that's exothermic. The heat of vaporization, when you're boiling again, or vaporization, it's positive because you're putting heat in, or if you're condensing, you're taking heat out, and that's going to be negative enthalpy. So the important thing is when you do a phase change, there's no temperature change. Whereas when you're talking about a system and the surroundings, you're using specific heat, that is a phase change. That's when Q will equal the specific heat times the mass times the change in temperature, which we had talked about this week. So different specific heat capacities. Notice gold is very small. So gold is going to change its temperature a lot higher, giving the same energy than aluminum. Aluminum is going to take more energy to change its temperature for the same amount of energy. So metals don't generally require much heat. They heat up easily. But water, 4.184, is the specific heat of water. And it takes a lot of energy to make water change temperatures. If you look at ice as a solid, it takes less energy to change the temperature of ice. And if you look at gas, it also takes less energy to change the temperature of the gas, but it takes more energy to change the temperature of the liquid. So we can find the heat of a substance loses or gains by using the equation for heat. Heat is mass times specific heat times the delta T. And again, you have to use it within the state of matter, solid, liquid, or gas, but it's not changing. If you have a physical change, you use this formula. Notice it does not have the delta T. It's just mass times the enthalpy. So you use that between two states of matter or during a phase change. So just to remind you what all these variables are, Q is the heat in joules. M is the mass in grams. C is the specific heat, joules per gram degrees Celsius. Delta T is the change in temperature, and delta H is either the heat of vaporization or heat of fusion. Okay, so this is called a heating curve. When you're heating, you're going to start here as a solid. You can go up. This is the phase change, solid to liquid. Notice how the temperature is constant. Then everything becomes a liquid. The temperature is changing. At the phase change liquid to gas, the temperature doesn't change. So at all these slanted lines, you're going to use this equation here, where the change is in temperature. So these are the slanted lines. Whoops, still don't look very well. But this formula is going to be used on the horizontal lines, because all you need is the delta H and the mass. Your specific heat that you have to use on the slanted lines are specific to that phase. You use the specific heat of the solid on the lower slanted line, the specific heat of the liquid, and then the specific heat of the gas. And the vaporization, enthalpy of vaporization, is what you use for liquid to gas. Enthalpy of fusion is what you use for solid to liquid. Okay, so as you increase temperature, you're increasing the energy. If you decrease, if you start off from a gas, you're going to decrease the energy. So in this case, you have to put in energy. So these will all be endothermic. They'll be positive heat values. When you're going from a cooling curve, they'll be exothermic. You'll be taking out heat. Okay, so using heat capacities. Q in joules, mass, there's the heat capacity in times the temperature. Notice how the units will cancel, and Q is in joules. You could remember this formula by saying Q equals mcat. So heating curves, the temperature changes within the phase. So within the phase, remember, when you increase temperature, you increase the molecular motion. And it depends on the heat capacity of the phase, heat capacity of solid, liquid, or gas. So each particular phase has its own heat capacity. And like I said before, the liquid is the most gas.
Oh, what a world,
So the solid to the liquid to the gas, you have to put in energy. So when you change phases, you're changing the molecular arrangement, how far apart the particles are. This is potential energy. So this first one, when you change temperature, is kinetic energy is changing. When you change phases, you're changing potential energy. The temperature remains constant. Particles aren't really moving any faster. It's just the particles are either farther apart or they're closer together. So the potential energy changes the intermolecular forces, those forces that hold those molecules together. So when you're going from a solid to liquid, notice the heat of fusion is 333 joules. Solids and liquids, the particles are relatively close together for both of them. But look how big the energy is, the heat needed to go from a liquid to the gas. Lots more energy to change the position of that's the potential energy. The liquid particles are close, the gas particles are very far away. So you have to put in a lot of energy. Okay, heating curves from ice to steam, 5 easy steps. You first have Q1. Q1, you heat the ice to 0 degrees C. That is where the phase change happens. Q2, you just melt the ice at 0. That's the phase change. Q3, you heat the water from 0 to 100. Q4, you change the phase, and it happens at the phase change temperature, 100 degrees. And then the last one is you heat the gas above 100 degrees. So you have 5 stages, 5 little segments of the heating curve. When you're changing the temperature, heating the ice from minus 20 to 0, you need the delta T with your heat capacity of the solid. When you're just melting the ice, notice the temperature is the same. You don't need a delta T. You just need your enthalpy of fusion times your mass. Notice they all have mass. All these equations will have mass. When you heat the water from 0 to 100, you need the heat capacity of the liquid and you need the delta T. When you're boiling the gas, notice you have a constant temperature at 100, so you don't need delta T. You just need the enthalpy of vaporization. And when you heat the gas above 100, you'll need the change in temperature. You're changing temperature, you have a slanted line. So to get the total heat from the ice all the way to the steam, you would have to add all these individual heats up. All right, let's practice. How much energy is required to heat 12.5 grams of ice at minus 10 to water at 0? So here's your start, 12.5 grams of ice at minus 10 to water is at this point in the curve. So you first have to heat the ice from minus 10 to 0. You're changing the temperature. You would need your mass times the specific heat of the solid times the change in temperature, 0 minus the minus 10. (259.63 joules. When you melt the ice at 0, remember you're not changing temperature, so all you need is the heat of fusion. And you're putting energy in, it's a positive number. Notice you're putting energy in, it's a positive number. So your total will be, you would add 259.63 to 4162.5 and get the answer. Notice that your Q values are positive because heat is added in, that's endothermic. Here's another one. How much energy is required to heat 25 grams of ice at minus 25 to water at 95? So you try to figure out where your beginning point is and where your end point. 95 is right below the change of phase, so you're still going to have water. So Q1, you're going to heat the ice from minus 25 to 0. Q2, you have to melt the ice. And Q3, you're going to heat the water from 0 to 95. Okay, Q1, again, you need your mass, the specific heat of the solid, and 0 minus a minus 25. The second one, you're going to go ahead and you don't need the delta T, you just need the heat of fusion, 333. And then the last one is the 25 grams times the specific heat of the liquid and your final temperature minus your initial temperature. In order to get them all, you have to add all three of them together to get the total heat. All right, a third one. How much energy is removed to cool 50 grams of steam at 115 to ice at -5? Okay, so this we're going the other way. Notice this is where you're starting. And you're going to finish all the way down here. So you first cool the steam. Notice there's a change of temperature. You need the heat capacity of the steam. When you condense the steam, you don't need the change in temperature. You just need the heat of vaporization. Cooling the water, you're going to need the heat capacity of the liquid. Freezing the water into the ice, you just need the heat of fusion. And then cooling the ice, you'll need the specific heat of the ice. So plugging in those particular, notice you have your delta T, your 100 is your final temperature minus your initial temperature. Notice how that makes that negative because you're releasing heat. When you condense the steam into liquid, this should be a negative because it's exothermic. When you're cooling water, again, you'll take your final minus your initial. That will give you a negative temperature, exothermic. When you're freezing the water, it's a minus because, again, it's an exothermic process. So all of these will be negative. And then the final thing is cooling the water. So the important thing is you have two different types of equations depending on where you are on the heating curve. And you add up all the heats to get the total heat. Okay, let's talk a little bit about food. It shows you the joules per gram, the calories per gram. 1 calorie is 4.184 joules. And 1,000 calories is 1 big calorie. We talk about small calories for science, but on your food wrappers, they talk about big calorie, which is really a kilocalorie. Does water really have negative calories? How many calories would you burn by drinking a liter of water? Initially at 36.5 Fahrenheit. Assume your body must expend energy to heat the water to 98.6. So you would have to first change your temperatures. So you're looking at your final temperature being 37 and your initial temperature being 2.5. You use the density for water. You're going to use the mass of water times the specific heat of liquid times your delta T. Okay, and what are you doing? You're starting initially here and your water is increasing in temperature, so you have to expend energy. So it's a positive. It's an endothermic process. So you have this many joules, you can convert it to calories. Divide it by 4.184 and convert your calories to so it's 35 calories. If you have cold water that you drink, you're going to have to expend energy to warm up that water. So what will happen over time if you have hot water here and cold water here? Your hot water is moving fast, your cold water is moving slow. But the collisions are going to eventually make the water go the same speed. So you saw this in your lab using a little calorimeter. Similar. We're assuming that no heat can be lost. So Q absorbed is going to be the Q released. So the heat absorbed in the water is going to be equal to the heat that was released. So these are called heat exchange problems. So Q of X is going to equal negative Q of Y. So here's a heat transfer problem. 75-gram piece of lead is initially at this temperature, 435, and it's set into 125 grams of water. The water initially was at 23 degrees. What's the final temperature of the mixture? I would suggest that you always write down what you have in the problem. Your lead has 75 grams. It's at this temperature, and you know the specific heat is 0.130. Your water is 125 grams, 23 degrees C, and your specific heat of water is 4.184. So they reach the same temperature. What is that final temperature? So the heat that's released from the lead is going to be the heat that's absorbed in the water. So they're both changing temperatures, so you have to use MCAT, MC delta T. You have to plug in the known information for both sides to get the final temperature. All right, so how do we do this? The water is going to be MC of water times the change in temperature of water. Remember, the change in temperature of water is initially at 23, and then you're going to have, it goes to a final temperature, which we don't know yet. The mass of the lead times the specific heat of the lead times that change in temperature. So you can set these problems up and you use TF for the final temperature. And then it really becomes an algebra problem. Okay, you want to make sure that you multiply these together, and then you'll multiply them by TF. That's 522.5 TF. And 522.5 times 23 is the 12,017.5. So you multiply these together by TF, and then you multiply them together by that. You distribute them. Okay, so what you have to do is you have to combine both TFs, and you want the TF on one side and the numbers without the TF on the other side. Isolate the variable. So once you get the TF on one side and the number on the other side, you just need to divide to get the TF. So 30.5 is the final temperature. All right, one more. A 95-gram sample of gold at 785 degrees C is dropped into 325 grams of water. It tells you the initial temperature of the water. It tells you the specific heat of the gold, and it's asking you for the final temperature. So again, you want to make sure what the temperature of the gold is, what the temperature of the water is, the heat that is lost from the gold is gained in the water. So the negative sign would be on the gold because it's giving off heat, and the positive sign would be in the water. If you first set up your equations like this, you'll have a lot less chance to actually make mistakes. So your specific heat of water is 4.184, the mass is 323 grams, and your change in temperature is T final minus 15. On the gold, your specific heat is 0.129, the mass is 97, and your final minus the initial temperature of. You'll go ahead and solve that algebraically, and you'll finally find the temperature is 22.1. All right, see if you can do this one by yourself. Notice one beaker of water is 13 degrees C, and the other beaker of the water is 72 degrees C. So the water that's hot is going to give off water that's cold. You do basically the same, and you can find the final temperature. I would again practice these problems so that you know how to do them. This one is different. It's giving you the final temperature. This is the final temperature for both the water and the iron, and it wants you to find the mass of the iron. So this is a new one that you have to, you're just going to use a little differently. The temperature of the iron is 500. You don't know the mass. Into the water, again, the heat that's lost of the iron is going to be gained in the water. Make sure the heat that's lost has the negative sign. So you don't know the mass here. That's what we're looking for. But we have the specific heat of iron, 0.4495. We have the specific heat of water, 4.184. We have the mass of water, 240 grams. We have the change in temperature. The trick is the change in temperature. You have to use the final temperature for both of them. So your final temperature, 42 minus 500, will give you the negative sign here. And on the mass side, on this side, you'll have your final temperature, which is 42 minus 20, will give you a positive temperature here. So notice you have a minus sign and a minus sign, and that will equal a positive sign, and you're solving for X in this case. So X is 107 grams. This is find the equilibrium temperature. That is essentially the final temperature. You have the ice is going to equal the water that's given off. The heat is going to go from the water to the ice cube. Remember, the water is at the higher temperature, so the heat flows from the higher temperature to the lower temperature. So your heat is going to be negative for the water. So your temperature, 98.2 grams of the of the water, 4.184, is the final minus 84. Now, if you look at the ice, you had 23.6. You have to use the specific heat of the ice and the final temperature. You also have to use the mass of the ice times that. This is the delta H, remember, of fusion, because you have a phase change here. So you need to include that for the phase change. And then the ice is going to go from 0 degrees to the final temperature. So this delta temperature is minus 31 to 0. And then it's going to change phases, and then once it gets 0 to the final temperature. So you have to set those equal together, and then you combine your final temperatures in algebraically, and you can figure that out. Here's some challenge problems. I would go ahead, if you want some extra credit in this unit, to go ahead and write these on paper and turn them into OneNote. And I'm giving you the answer, but you have to show me all the work. You should be able to go ahead and draw a heating curve. And make sure that you know which part of the curve has which equation for it. Okay, so that is the full heating curve. All right. Okay, occasionally your delta heat of fusion is given in moles, so you would have to convert your grams to moles using the 18 grams per mole for water. And also the heat of vaporization. Sometimes it's given in joules per mole instead of joules per gram. You just have to watch the units and use the correct value.